Hello, everyone, and welcome to this lecture in the Hands on Large Language Models series. In the previous lecture, we looked at the difference between generative large language models and representation large language models. We saw that generative models were decoder only and representation models were encoder only. We looked at BERT as one major model in the representation category, and we looked at GPT as a major model in the generative models category. We also looked at this LLM evolution tree, where we saw the difference between open source and the closed source LLM. So, just to recap, here's the difference between open source and closed source LLM. So, with respect to closed source, we need to access the large language model through an API, and the code and the architecture of the large language model are not shared by the user. This is typical of GPT 3.5 and GPT 4 as examples. However, open source models can be directly run by the user on their local machine. They can be run by the users on the cloud, such as Google Colab or Jupyter Notebooks. We don't need an API to query the LLM itself. More than that, the code and the architecture of these models, such as what are the weights of the different transformer layers, what are the weights of the, let's say, embeddings, all of these parameters are shared with the user. So we can even make tweaks and we can fine tune. So it's generally better for research purposes. These are open source models. Okay, so that brings us to today's lecture. The main goal of today's lecture is that we'll be generating our first text using an open source large language model. So what we'll be doing is that we will first download an open source model, then we will run the open source model, and then we will give it a query, and then we'll check the response. This is one of the simplest workflows for dealing with open source large language models, and I want to show this to you in a lot of detail so that you understand every single aspect of it. When we download this open source model, we'll be using a cloud based framework called as Google Colab. I'm sure many of you are aware of this. All of you just need a Gmail account to replicate what all I'm showing in today's lecture. In addition, what I'm showing in today's lecture, you don't need a GPU to run that code. Even if you have CPU access, you can run it. And Google Colab provides free GPU access to a certain GPU. I think that is called as T4 GPU. So let me check. Yeah, if you see this T4 GPU, Google Colab provides free access to that. So you can switch to that. I think that's actually better in terms of running this model, and you don't need to pay or anything for it. It's available for free through Google Colab. Okay, so let's get started with this implementation. It's going to be very exciting when you see the results in front of your eyes. It's very different than using GPT. So if when you use Chat GPT, for example, you don't code anything, right? You don't use Google Colab. You don't use Google Colab at all. You just go to their interface, you give a query, and then you see a response. So this almost feels like a black box. You don't know what's going on internally. But as you will see right now in today's lecture, we'll open this black box and we will see what all happens inside a large language model, and you will see how easy it is to run and deploy this on your own local machine through Google Colab. Okay, so your first question would be that, okay, we have to use an open source model, but where do we find and download the large language model from? Where do we get the model itself, and how do we bring it to Google Colab? This is where I want to introduce you to something which is called as Hugging Face Hub. So Hugging Face Hub is that place where we can find almost any open source large language model, and we can download the model from this particular website. So I'm just taking you to the Hugging Face website right now. This has become extremely famous. It was already popular before, but ever since the launch of large language models, it has become hugely popular, not just for LLMs, but for other types of machine learning as well. So this is a platform where machine learning community collaborates on models, data sets, and applications. All of the models on Hugging Face are fully open source. So here you can see there are the Llama models, which are fully open source. And today we are going to use a Phi-3 model, which is also open source. So it's one of the best communities for also getting to learn about other models which are being released, getting to learn about other open source models. And when you learn how to download open source LLMs from Hugging Face into Google Colab, you can essentially use that same workflow for other large language models also. So the code file which I'll be sharing in today's lecture can be used for any large language model which is open source. So that's the first thing. We are going to download the large language model from Hugging Face. And we have two choices, right? Either we can go ahead with so let me use a different ink here. Either we can go ahead with representative models like BERT, or we can go ahead with generative models. In today's lecture, I am going to show you generative model implementation, and the large language model which we are going to use is Phi-3 Mini. So when I say Phi-3 Mini, you can immediately Google this. So Phi-3 Microsoft, and then you will see that here is the Phi-3 Mini, and let me open some links with respect to that. Here's the paper which was released by Microsoft regarding Phi-3. It's an open source model, and the entire model is available to download on the Hugging Face website. So especially we are going to use this Phi-3 Mini 4K Instruct. What does this 4K and what does this Instruct mean? We'll learn about that when we start looking at the code. But for now, you need to understand that we are going to use the open source model developed by Microsoft called Phi-3, and it has 3.8 billion parameters. We are going to download it on our Google Colab. We are going to query with a question and then we'll get a response. All right. So compared to other large language models such as let's say GPT, for example, GPT-3, the largest one had I think 175 million parameters, 175 billion parameters. So let's check this actually. GPT-3 size. Yeah, so the largest GPT-3 model have 175 billion parameters. So compared to that, this is pretty small. This is the model which we are looking at right now is 3.8 billion parameters. So again, as I mentioned yesterday, whether this comes under the small language model category or not is still up for debate. One can say that, well, it's almost 100 times smaller than GPT-3, so it's definitely a small language model. But someone else can say that compared to 1 million parameters, 1 billion is still pretty high, right? So it's it should still be called as a large language model. But anyways, the number of parameters is relatively small compared to GPT-3. That's an objective statement which we can make. And with this, let's jump into code right now. So here is the Google Colab code in which I have written the entire implementation, and it's very small, but I want to explain everything step by step so that nothing is left out. I will make sure that not a single line of code is not understood by you. So I won't just be going through the code quickly. I will explain every single aspect. Okay, so the first thing is that we have to install two libraries. The first library is transformers and the second is accelerate. When you run such codes, immediately you should first search about, okay, what do these libraries mean? So here I have opened the transformers library for you. It's developed by Hugging Face, and a huge number of researchers all over the world have been using this library to load transformers and to run large language models. It's one of the most famous and popular libraries. So we are going to uh, basically install this package because that will allow us to load the large language model itself. This is the first package which we are going to install, and the second is called as accelerate. So what accelerate does is that it's essentially used for parallelism. So if we are as you can see here, as the model gets bigger, parallelism can help to increase this training speed by several order of magnitude. So let's say, for example, if you have a distributed setup, whether it is multiple GPUs on one machine or multiple GPUs across several machines, you can use this accelerate framework to do parallel computing. I don't think it is too much necessary in the current code which we are implementing, but just you can have it so that it replicates what all we will implement in the subsequent code blocks. I also want to tell you a bit about this model itself. So before running the rest of the code, let us go through this model and try to understand. One thing we have understood that it's 3.8 billion parameters. What is this 4K? So it turns out that 4K is the context length, and context length means it's a model which essentially generates new token, right? Context length specifies how many maximum number of tokens the model looks at before predicting the next token. That's the context length. So with the mini, we have 4K, which is it can look at 4,000 tokens at max to predict the next token. And what is instruct? Instruct means that this model is not just pre-trained; it's actually fine-tuned on an instruction data set. So let's go to that portion of the documentation. Yeah, so the model is first pre-trained and then it's fine-tuned with supervised fine-tuning, which means that after the pre-training again we give it labeled data, or we give it instruction data saying that if this is the instruction, this is should be the output, if this is the instruction, this should be the output, and we fine tune the model so that it becomes good at responding to instructions. Just a pre trained model does not do well at responding to instructions. And since the main goal for us at the end of this lecture is to query the model and get a response from it, the model should know how to follow instructions. So we have to fine tune this LLM later. And that's why the name has instruct 4K instruct, which means that we have fine tuned this model on a specific instruction data set. All right. Another thing which you can actually understand from this documentation is how much time it took for Microsoft to train this model itself. So to pre-train the model, it took about 10 days, and the training data is 4.9 trillion tokens. So look at the data set which they have used. It's huge amount of data, and that's why it has taken 10 days on this GPU, which is hugely powerful. And some of the data set which they have used are publicly available documents, newly created textbook like data for teaching math, coding, common sense reasoning, high quality chat format, supervised data. So this is the instruction specific fine tuning which is done after the pre-training. In the code, you can search for data set, and if you are interested, you can dive a bit deeper into what exactly is the data set which they have used for the pre-training itself. Okay, so that's what we understand about the pre-training time. And then one more thing which we can look at is the specific format in which you have to query. So they have a specific format in which you have to chat with the model, and in the format you have to assign the role. So you have to say that the first role is the system, and the system should behave like you are an helpful assistant, and then the user should ask a question. So we have to give roles. So for system, we have to say that you have to behave as an assistant, or you have to behave as a chatbot, or you have to act like a person who is responding to an email. And then in the user, we have to write the specific questions, such as write a draft or write an email to this person in a specific format, etc. So, for example, here is one way in which we can interact with the model, where first we have to specify that for the system you are a helpful assistant, and then the user. So, this is our actual question: how to explain internet for medieval night. So, when we will query the model later, we'll have to give the input prompt in this manner, such as system and user, and then we will get a response. So before jumping into the code, it is always very important to understand a lot of things in the regarding the documentation itself. That also makes you a stronger LLM and a machine learning engineer, because that way you know many more things about why you're running the code rather than blindly running the code. Another thing to mention is that tokenization. So every model uses a process of tokenization, which means that what is the vocabulary size, and whether it's a subword tokenizer or whether it's a word based tokenizer. So Phi-3 Mini 4K has approximately 32,000 tokens, and this is the same tokenizer which was used by Llama 2. Now, if you look at GPT-2, GPT-2, GPT-2 vocabulary size, this is 50257, but the tokenizer which we have used for Phi-2 is much smaller. The vocabulary size is much smaller. It's 32,000 tokens, and this is a subword tokenizer. So just one word is not equal to one token. We may even have one character as one token, and we may even have subwords as tokens. This is similar to what is implemented in GPT-2 as well, and we'll see this in the code itself. But for now, you can try to see how much I've tried to explain through just going through this data set. So without even running a single line of code, you can go through this documentation and try to understand many things. Okay, so after executing the first line, now we are ready to go to the next code block, where from the transformers module we have to import two packages or two modules. First is auto model for causal uh, language models, and second is auto tokenizer. So as I've written in the whiteboard itself, when you use an LLM, there are two models which are loaded. There is the generative model itself, which is Phi-3 in our case, and the underlying tokenizer. So we saw that the tokenizer has approximately 32,000 tokens, right? So the tokenizer is loaded. The reason it's called auto is that we just need to specify the model name or the large language model name, and then the model is automatically loaded. The entire architecture is automatically constructed. How many transformers we need, how many attention heads are there in each transformer block, etc. And even the tokenizer. So you first have to define model equal to auto model for causal language models dot from pre-trained, which means that we are using this pre-trained model released by Microsoft, which is called Phi-3 Mini 4K Instruct, and we are automatically loading the model, which is this. So the entire architecture and the weights are already loaded, which are the weights from the pre-trained architecture. Okay. And then what you can do is that you can mention this, that tokenizer equal to auto tokenizer dot from pre-trained. So here we are essentially saying that whatever tokenizer was used to pre-train this language model, we are going to use the same tokenizer. We don't want to change the tokenizer at all, and that's why it's called auto tokenizer. So you'll run these two, and then it may take some time for this model to load. So the biggest time sink is this 4.97 gigabytes and 2.67 gigabytes. So it might take around 8 gigabytes to download this, and depending on the internet speed, you'll have to reserve that much time. So I'm sitting in a place where the internet speed is around 100 200 megabytes per second, so it's pretty fast. But I really recommend you to sit in a place with a stable Wi-Fi connection so that this model downloads. This is the most time consuming step of the entire code. After that, everything is pretty fast. But the only thing which you will need to run this code is to sit in a place which has good internet or good Wi-Fi connection, and then it should run in a pretty smooth manner. So after you run this, you will see that you will see all the green progress bars here, which means that the model is, it will first load the model, and then it will load the tokenizer. So we are loading two things here. As I've mentioned on the whiteboard, when you use an LLM, there are two models which are loaded, the generative model and the underlying tokenizer as well. All right. So then what we can do is we can understand a few things about this tokenizer itself. So you can print out the vocabulary size. You can say tokenizer.vocab size, and you will see that the vocabulary size is 32,000, which is what we had written on the whiteboard also, which means that there are 32,000 tokens. So let me take some words and let me encode these words using this tokenizer. So I'm taking words hello, world, AI, and learning, and I'm encoding it with the tokenizer. So here you see the tokenizer for hello is just one token ID. For world, it's one token ID. For learning, it's one token ID. But for AI, you see there are two token IDs. This is the first indication that this is a subword tokenizer. So A, which is the character, might be one token here, and I, which is the second character, might be the second token. I can even tokenize complete sentences. So here I am taking a sentence, artificial intelligence is transforming the world, and I am saying tokenizer.encode this sentence, and then I'm going to decode this encoded sentence. So when you do tokenizer.encode, you will see the original sentence, artificial intelligence is transforming the world, and then here is the tokenized sentence. So you have token IDs, right? Okay, so if you count the number of words in the original sentence, artificial intelligence is transforming the world, there are six words, right? But if you count the number of token IDs, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 token IDs. So this is another proof that it's a subword tokenizer. In fact, what I've done in the next code is that I have actually taken this sentence and I have mapped it to the token IDs corresponding to the particular word. So, for example, with this, here you can see that First, I get the encoded sentence, and then I've decoded each token ID back to its respective token. So, what I've done is that when you have these token IDs, can we construct back the token? So, now you will see that for 3012, that's the first token ID, that is for art. Then 928 is for IFIC, IFIC. Then 616 is for IAL. INT is another token. Allegiance is another token. So this is the sign that this is a subword tokenizer, right? And that's why there are so many token IDs. The reason I do these exercises is because it peels the layers a bit, and makes makes you a better engineer, because you don't just run the code, but you're trying to understand, okay, I load this tokenizer, can I learn a bit more about this tokenizer? And then you see that, okay, here is a subword tokenizer and here's how it works. So now you will never forget the difference between word tokenizers and subword tokenizers. Great. Now what we can do is that after the model and the tokenizer are loaded, we can construct a pipeline for generating the text. So the reason we do this is that it just makes it easier to just pass everything into this pipeline. So pipeline is another module which is given by Hugging Face, and what we can do is that in the pipeline we can pass different things, such as we can pass the model, we can pass the tokenizer which we have loaded before, and then what we can do is that we can say return full text equal to false. The reason why we say return full text equal to false is because when we print the output, we don't want the prompt to be printed, we just want the response. That's why we say return full text equal to false. And then max new tokens equal to 500. This limits the output a number of tokens generated. And do sample is equal to false. This is a sampling technique. So when the next token is predicted, it just chosen from the maximum probability of all the tokens. We don't use any sampling. So there are some other things such as temperature scaling and top case sampling, where you use a multinomial distribution to sample the tokens so that the output becomes more creative. We will learn about that in subsequent lectures in this series, but for now you can just keep in mind that this do sample make sure that the next token which is printed, the next token which is printed is the one which has the highest probability. So we don't, it's a deterministic prediction. We look at all the tokens and their probabilities, choose one with the highest probability. We are not using a multinomial distribution here. So you can run this now, and then you can see that the pipeline has been created. Now all we need to do is that we need to pass some messages into this generator, and the output will be printed out. So then the next question is, how do we pass the input prompt? So here, if you remember what we saw, there is a specific format in which we have to pass the input prompt. And so here we have to specify the role, and then we have to specify the prompt. So what I have done here is that the first role is the system, and I want the system or the LLM to be a stand-up comedian, and the second is the user, the second role, and here is my actual prompt. And here I've written create a funny joke about chickens, and then you can run this, and here you can see that the output is generator, and then you pass the messages. So then the output is printed out, and the output is that here you can see that a funny joke has been created by the large language model. Why did the chicken join the band? Because it had the drumsticks. I did not like this joke too much, but it's a great proof that we have successfully downloaded an open source large language model. We have passed a query to this large language model, and we have generated the output. That's exactly what we wanted, right? And now imagine the kinds of things you can change with this. First of all, you can change the model to whatever you want. We just loaded Phi-3 mini because it's a bit smaller, and that's why it does not take up too much space, it does not take up too much time to load. But you can load any open source model on Hugging Face. Then you can pass in different messages here. You can even give different prompts. As you can see in the documentation over here, you can be a bit more creative with respect to the prompting, and then you can see the results which have been generated for yourself. So that brings us to the end of this lecture, where we demonstrated a simple code which shows how to download an open source large language model, how to use Hugging Face, how to dive a bit deeper into the tokenizers which are used, and then how to generate text based on the particular prompt style. which that large language model prefers, and all of that is given in the documentation of the model itself. As this course progresses, we'll take much more complicated examples, but as you see, this course is much different than the build a large language model from scratch, because here we have already started the coding process, already started applications, already started using open source models. I hope you are liking this series, and we'll dive a lot into a lot more practical aspects subsequently. But I'll continue following this whiteboard approach along with the coding approach, so that I don't want to blindly take you through the code. I also want to explain to you the theory, or some basic theory and intuition behind which, or why the code is working the way it is. Thank you so much, everyone. I look forward to seeing you in the next lecture.